الرحيم. Nous assistons aujourd'hui à la soutenance de thèse de doctorat intitulée Investigation of Relaxation Methods and Iterative Schema Befitting Matrices of Bounded Linear Operators, présentée par le doctorant محسن sous la direction du professeur Mohamed de l'Université de l'Alma et le docteur Khalaf de Constantine, comme examinateur, professeur Lahsen Shorfi de l'Université de l'Alma, Gebay Hamza de l'Université de l'Alma et Tarchir de l'Université de l'Alma et moi-même, de l'Université de l'Alma. Donc, vous avez 40 à 50 minutes pour exposer l'essentiel de votre travail.
Assalamu alaikum. خلينا نعاود بالانجلي. Peace and blessings of Allah subhanahu wa ta'ala be upon you all. Today, in this hallowed amphitheatre, and from behind this podium serving piece of furniture, must I stand before you all, with esteemed jury panel, to defend my PhD thesis, bearing the title, Investigation of Relaxation Methods and Iterative Schemes, Befitting Matrices and Bounded Linear Operators. Over the course of the past 3 years, at Laboratoire des Mathématiques Appliquées et de Modélisation, with feet crossing miles over the Mediterranean, I have had the privilege to conduct my degree's research under the supervision of to reiterate, my sage and poised supervisor, respectful Professor Mohamed, alongside the close accompaniment and the unwavering support of the lively, respectful Dr. Khalaf. With no further delays, I invite you all, respectful panel and audience, to please allow me to begin my defense as it unfolds. In the name of Allah, I am a mere person. Occasionally, I'd keep memory records of sayings of people from around me. Believe me, they really end up being very influential in recalibrating my saying. An example of this should be a recurring conceptual word, emphasized by a former professor of mine. Reassuringly, I've embraced it for a motto all throughout my PhD degree. It goes as, convexity is a very crucial property in mathematics. It comes at the very forefront of the delicate aspects associated with Hilbert spaces that, strikingly, may almost always be identified with L2. But then, do you happen to possess convex brains? What is essential for a mathematician is to cultivate a sense of intellectual convexity. Strive to connect ideas, please. My former professor. Surely, we will attempt connecting ideas. Disclaimer. Given the extended duration of the defense, please be alarmed that occasional omissions of some content and deliberate jumps over certain technicalities may occur. Proper indications of their precise locations in the supporting manuscript shall be provided. Thank you. Historical traces. Being impossible to enchain from the present to future, it never fails to look back into the past for insights. Fourier, published in the 19th century, an era nothing less than a buoyant cauldron of scientific advancements. Fourier's Théorie analytique de la chaleur was a gem on its merits in the treatment of heat propagation associated problems, as well as the employment of the trigonometric pair of sine and cosine, to decompose nearly all sufficiently well-behaved functions encountered in many real scenarios. Addressing the continuum, the investigations that followed made possible the transition from Fourier's original framework to a broader terrain, where, named after him, The Fourier's integral transform has since become a staple in the study of PDEs, the setting of their analytical solutions, or the accentuation of their link with ODEs, and rightly so. In a cradle of differentials it was. Keeping with history, a zoom into the timeline shows how Fourier's decomposition idea, although novel in what it used, was not alien to what mathematicians considered at the time. For it mimicked the use of Lorentz series method to solve differential problems of origins in physics, a process leading to the consideration of infinite determinants, predating the ripening of linear algebra on the hands of many contributors, including Gauss with his brilliant process of iteratively relaxing an algebraic linear system in order to solve it. Infinite determinants were the tools harnessed by Fredholm in his crafting of his notable works that followed his coming into contact with other fellow European mathematicians, like those of France in particular. Yet, it was contemporary to the works of pioneering mathematicians like Poincaré who sought the interrelation between PDEs and what we know as integral equations. Fredholm investigated his equation of the second kind, equation number 1, in the inner function phi. Beyond the fragments, by the late 19th century, the mathematical community converged towards a rather systematic rigor of knowledge treatment in place of the previously adopted loose jargon, as well as favouring of abstraction, making it a fertile soil for Fredholm's concepts to prosper, luring more people towards integral equations, of whom Hilbert and Schmidt were the most influential. Not only was Hilbert's instance of fragmenting the closed interval 0,1 into finitely smaller chunks, then alternated integration into, or to summation, an active element in how the establishment of function analysis and emergent separate knowledge at the time was initiated, but also made it viable for an option to later harness the potential of the unconventional machine computational powers to set record resource savings when computing the approximate solutions to equation number 1. For a richer historical account on the panoply of these interconnected mathematical endeavours, kindly refer to any historical work of your choice. When namely we have personally grown fond of, it's an article, it's reference number 1 of Mr. Berger. Iterate, in a century unfolding in adverse turmoil and restlessly tensioned order, the use of computers to approximately solve algebraic linear systems of the form 2 fostered an intense competition to date on who converged faster to solutions of 2. Justifiably, with all the possibilities offered by computers' mind, big N, parameter big N, is desirably destined to grow bigger. Hence, Gauss, Jacobi's, and their peers' iterative processes of the old times found applications in the new scheme of events. Indeed, at the intersection of computer science and mathematics, algebraic treatments of approximating solutions to differential problems of various kinds have been evoked too, where softened. By the 1950s, the relaxation concept was crowned in the addition of a parameter omega that made it even more flexible to adjust the convergence discussed according to how one so pleases. A detailed approach may be referred to reference number 2. It's a book, and it's not a book, actually. It's a preprint article, it's Mr. Sad. You may also compare the thesis manuscript, chapter 1, section 2. A share for integral equations. Sharing the depths provided by differential equations, integral equations did not lag behind on the race aforementioned. In his personal perspective, reference number 3, Atkinson created his joint of the many different ways researchers brought solving integral equations, including the modern form for our target equation 1, about eventually treating systems in the format of 2. By whichever transitional method from 1 to 2, for all that we care, the premise has always been to proceed as, provided its solvability, tend to the notorious integral term of 1 and try approximating it. In fact, adequately create a discrete quantity out of it. I should actually move it here. of course. Then using this, build your version of the form 2 with a proper iterative scheme. Use the machine to iteratively, approximately solve the system created. In so many cases, you've finished and are good to go. A period too long. The algorithmic process we have just discussed withstood for some long time, for decades or even a century. Perhaps it was about time for some change given all the promised benefits of diversity, but what could possibly motivate that? Dawn of the 21st century. In his treatment of the generally static, stratified, atmospheric, stellar energy transfer boundary value problem, which invoked dealing with weakly singular linear Fresnel integral equations of the second kind, it's mouthful. Olivier Tito concluded his thesis, reference number 4, in the following statement. Ce point de vue nous a d'ailleurs poussé à étudier et mettre en œuvre des méthodes asymptotiques efficaces pour essayer de surmonter les difficultés majeures de ce problème qui réside dans l'amplitude très importante de l'intervalle d'intégration. Olivier Tito, PhD thesis. It originated elsewhere. Non-linearity, in their paradigm shift made in 7, reference number 7, the author's theoretical investigations culminated in uncommonly demonstrating that to approximately solve non-linear equations, abstractly set over Banach spaces, then to linearize first and discretize second instead of the reverse, proved numerical plausibility and a mistaken superiority over the accepted methods. Hence, at Elman, it was questioned whether this counterintuitive slight alteration of conventions could also work in other plots. Mathematics, patterns. In particular, given the mentioned motives, Mr. Sami Lemita and his co-authoring panel, targeting a linear Fresnel integral equation of the second kind defined over a large real interval, closed interval AB, which is the equation number 3, has questioned whether a similar bold alteration of the process of slide 23, by iterating then discretizing, would be associated with a similar scale of benefits. With stable quadratures, what would be of the conditioning kappa mentioned in the thesis manuscript, chapter 1, section 1? Patterns, success. Fortunately, the conjecture was grounded, leading to a couple of articles and a PhD thesis, reference number 8. Carrying the torch. Genuinely, their work combined a devotion for computational resilience and a solid treatment of theoretical aspects, giving rise to the promising potential for which our two-part presentation today comes to defend our carrying on of the investigation of the depths of the approach. Okay, the footnotes technically offer 3.5 parts, with a half being the inevitable interlude to the part to come. Keep an eye for it. Keep an eye for it. Notice, for all intents and purposes, we shall keep excluding the preliminaries from the presentation with no disregard to proper referencing. Therefore, kindly keep your paper digital version of the thesis manuscript within reach. Thank you. Part 1. The truncated series of operators. Based on a published peer-reviewed paper, reinstatement. Over large real interval, closed interval AB, we reinstate for non-zero real parameter lambda, and by continuous state functions, K and F, the linear, regular, second kind Fresnel integral equation number 4, of the unknown function phi. This is not the same phi as before. Unspoken facts, inevitable to mark down. In literature, Paul boasts an extensive share of studies. In fact, Atkinson's, reference number 9, encapsulates almost all that surrounds it in much obliged elegance. As far as Paul's unique solvability is concerned, it is known that, equipped with the uniform convergence norm, the infinity norm, the Banach cyclography on the Banach space makes a ground for the compactness of the integral endomorphism, the endomorphism A, which combines with the condition number 5, to yield the desired results by Fresnel's alternative theorem. The fleshing out of the steps in slide 23 for 4 makes the substance of many literature references like Atkinson's, which is reference number 9, that we have just mentioned, other entries found in the thesis manuscript, references, or even the brief retelling provided in Chapter 2, Section 1. The indispensable facts, the starting point. Sorry. Condition 5 is one that we should all bear in mind for as long as Part 1 extends in time. Starting point, of course. Following suit with meters 8, the alteration starts in considering one of definite integration properties. Indeed, for the big N parameter greater than or equal to 2, creating the mesh of knots x of I, as shown, makes for the transformation of 4 into the following linear system of French integral equations. We have given the system into a compact form. We didn't want to give it in a matrix vector form, but perhaps it's not needed. With the restrictions. Hence define the Banach space, C calligraphy sub I, and introduce the family of complex operators, A sub ij, where the operator norm of A sub ij is just defined as usual, using the sup, and is given by that formula. Next, Cartesian product Banach space, B script, with its norm as shown. It is then natural to have one's focus on the vector space, M script, which is identical or can be identified with the space of all bounded endomorphism of B script, which by the norm given is a Banach space. The identity operator matrix I of M is such that the entry ij, the ij entry is just the Kronecker symbol times the operator id sub ii. Excuse me, can I actually just look up? Abstraction. Consequently, transition from 4 to 6, where A calligraphy is just the data operator matrix, element of N script, big F and big phi are respectively the data and unknown function vectors, elements of B script. Similar to linear algebra, one is concerned of 6 unique solvability. Fortunately, 5 guarantees this by direct application of the geometric series theorem. We see that in 7. We can see why, because of 7. Moreover, together with Chapter 2, Section 3, Definition 2.3.1, which is the definition of strictly diagonally dominant by row operator matrices, the splitting shown before the wall, where D calligraphy minus E calligraphy minus F calligraphy are the diagonal, normally the strict lower and the strict upper parts of A, respectively, and the operator matrix norm does verify the inequality shown. All advocate for having the operator matrix lambda minus A calligraphy an STDR operator matrix, since we have this estimation. Thus rendering valid the generation of the generalized version of the iterative scheme of Gauss-Seidel, since the inverse operator matrix given exists by virtue of applying the geometric series theorem such that the mentioned scheme converges by means of Banach's fixed point theorem. We shall establish the component-wise version of GGS. It's 8. It's the scheme, the component-wise scheme given by 8. Next, in the alteration process comes the discretization, where for the index I running from 1 to big N, and N, the small n, an integer greater than or equal to 2, introducing the submesh. One is the submesh of the interval I. One is prompted to apply Nystrom's method to 8, approximating A sub I by a compact quadrilateral operator A sub IN. Noteworthy to keep in mind is that the operator norm of the A sub IN is given as follows. This is given in Atkinson's, I don't know which book, but I do think, yeah, I'm sure that it is given in Atkinson's books, but which book it has really slipped my mind. It is then the case that we obtain 9, the discretized version of GGS. Roughly, at this point, we've only retold a great part of the meter's contribution. However, it is that nostrums has a subtle convergence treatment where the family of operators A sub I in converges pointwise to A sub I over C calligraphy sub I. The same sequence converges not strongly to A sub I, but in a rather collectively compact manner towards its simple operator limit above. That we need to dedicate much care. Since the operators neighbouring an invertible bounded linear operator are themselves bounded and invertible, then the pointwise convergence stated here and before, and the fact that one chooses the sub to be finite to ensure the uniform boundedness of the family of operators imply that we could. Imply that we create a convergent scheme in N, with the inverse, with N, to exist starting at some large rank, N sub 0, very great than 2, and such that at any k greater than or equal to 0, at any step, at any iteration, we have the estimation for each component I running from 1 to big N. Despite a guaranteed, the truncation and clear applicability. Despite a guaranteed invertibility from large ranks, we cannot say that the geometric series theorem applies to the operator lambda minus A sub I n to write the corresponding infinite geometric series of operators. In essence, it is unclear whether we have this strict estimation. Positivity implies stability. Considering our time and fear of being drenched into the mutual area between probability theory and numerical analysis, we bring attention to the following. Assertion. In general theory, a family of real positive weights generates a stable quadrature rule to approximate a definite interval with a suitable function over a compactive R, provided that the sum of all the weights is equal to the length of the compact interval under scope. Of course, the previous assertion is not artificially made. The interplay between stable quadrature rules, the weights, and the nodes distribution over the integration interval makes a rich area that may still require more attention. One may refer to reference number 10, where de novo, the quantity kappa of chapter 1, section 1, plays a major role in such an investigation, proving in turn the given assertion. Consequently, we obtain lemma 1.1. Denote the resolvent set of. Denote the resolvent set of A sub I in by re of A sub I in, where re sub I in is just defined as C minus the spectrum of A sub I in. Then using stable quadrature rules for all rank n greater than or equal to n0 sub 0, with n sub 0 sufficiently greater than 2, the operator A lambda minus A sub I n is invertible with lambda in its resolvent set, its regular parameter, and we have the modulus of lambda strictly greater than the operator norm of the quadrature operator. Eventually, triple convergence theorem. Eventually, the previous lemma allows for certain that the inverse can be given approximately by the geometric series of operators given, which allows truncating in GGSN. We get 10, invoking the parameter P. Then the triple convergence result follows as theorem 1.1. Over the Banach space, script B, scheme 10 generates a function vector sequence, phi sub n, and with k and p, that convergence in the B script norm to the function vector phi, big phi, solution of 6, equivalently prompting the required data to build the solution of 4. Some numerics. At P is sufficient to explore the first example given in the manuscript, where for lambda is 400 and alpha being pi over 200 squared, one is given a regular, positive kernel, linear, second kind Fredholm's interval equation, as shown, prompting that an appropriate right-hand side source f for the exact solution, phi of x is just x, over the interval 0 to 200, is a continuous function, f, as shown, for h equals 1, and a tolerance of 10 to the power minus 8 on a 6th generation I5 BC with a finitely varying p. We obtain the two tables, the error in GGSN and the error in GGSN with respect to p. We can actually see that, I'm very sorry, we can actually see that they are almost identical with some benefits in the table corresponding to GGSN with respect to p. Consequently, although reliant on finite summations of a geometric series of ontomorphisms, the p truncations converge and offer some gains in time as well in their achieving the same rank of errors as is observed. A profit said to accumulate the more n grows. To say the least, it is in bypassing the inversion of relatively large algebraic matrices by means of computing a combination of their powers that such an endeavour stands out. More can be referred to in the thesis manuscript, chapter 2, section 5. End of part 1. Originally kept off the preliminaries of the manuscript and given the likelihood of their moderately advanced range, having implications in quantum theories that hold the interlude set apart of some very brief introductory notes on Banach algebras as well as C-star algebras are provided. Interlude. Dispose of the field K and a K vector space V. Then if the dot denotes an additional binary internal operation over V such that whenever we combine x and y, or y and x, we produce another element of V compatible with the intrinsic vector space structure V, then one defines a K algebra. Moreover, defining a norm application consistent with a dot operation defined previously to guarantee its continuity. Then one introduces a normed algebra where, assuming the completeness of its norm, the situation transcends to introducing a Banach algebra. Of course, it depends on the binary dot operations of whether V becomes a unital Banach algebra and or a commutative Banach algebra. Banach algebras have many hallmarks of their own, where, on a unital Banach algebra, an element X's spectrum set is a non-empty compacted K. On a unital Banach algebra, the set resolvent, or the resolvent set, it's interchangeable, which sets the stage for the topologically open algebraic group of elements of the unital Banach algebra. And the spectral radius of an element X on a Banach algebra, V, is defined as all of these definitions in what generalizes Gelfand's formula. Before we finish, note that exclusive to C, introducing the involutive star binary operation over the Banach C algebra W, where we have these three axioms, then we attribute W the quality of being a C-star algebra. For this, of the hallmarks would be the spectral mapping theorem, where given X in W, a C-star algebra, such that X is normal. It means it commutes with its adjoint. We have the spectrum of the phi of X is just the phi of the spectrum of X. This is especially applicable whenever phi maps from the C-star algebra into the polynomials over the C-star algebra, that is, phi of X is a polynomial function in X. An illustrative concrete example in these concepts would be the space of all endomorphisms over a C-Hilbert space H, denoted L of H, where equipped with its complete operator norm, it makes a non-commutative unital complex Banach algebra for the operator composition, and by the involutive adjoint operation, it wields the structure of a C-star algebra. Part 2. the GJOR. Please be alerted that, as declared in the manuscript, the current part is not based on a peer-reviewed work. More specifically, results discussed subsequently fall much more likely under the preprint category. Everything afresh. With some limitations and clear caveats, a promising potential has been offered by reference number 10. Adopting the alteration process within the same settings as demonstrated in part 1, the article was based on applying a convexity combination to generate the iterative schemes studied, thus introducing improvements parallel to those established in finite dimensions. More can be compared to Chapter 3, Section 1. We consider the same route, but walk it fundamentally differently. Over Lebesgue measured substantial length real interval omega, open interval, we consider for non-zero real lambda an omega square integrable environment and reintroduce the linear second kind Fredholm integral equation, equation number 11, in the unknown square integrable u, function u. Since existence and uniqueness, since it is historically established that compactness provides solution existence, it suffices the endomorphism K, I'm very sorry, I'm having a sore throat, to be Hilbert-Schmidt for the existence of U in L calligraphy, to follow having guaranteed the endomorphic compactness by further imposing that its Hilbert-Schmidt norm verify 12. The uniqueness of U follows for every F in L calligraphy. The dismissed convention. Of course, we shall carry on adopting the alteration process discussed all throughout the presentation. However, since it is L calligraphy, then the discretization is mediated by means of projections onto finite dimensional subspaces, particularly via applying the truncation endomorphisms onto the truncations of L calligraphy's Hilbert's basis of Legender's polynomials. Bear in mind that adopting the conventional steps places us before algebraic linear M systems where data matrices are symmetric by construction, thus rendering applicable the spectrum mapping theorem over the C-star algebra of C, the matrices of complex entries and dimensions n+1 times n+1. A result to corroborate both the unique existence of the approximate solutions and the convergence of the relaxation iterative schemes to be applied. For details, come for Chapter 3, Section 2. The alteration. Phase 1. The process begins when, for an integer n greater than or equal to 2 and excluding the endpoints a, b, the subdivision from part 1 is reused, leading to the linear system of integral equations for x almost everywhere in x omega sub I, and we have this component-wise equation, where k sub ij is Hilbert-Schmidt, mapping from L calligraphy sub j to L calligraphy sub I. By the inner product, the I inner product, the Cartesian product space, H script, is Hilbert for the inner product given on the slide. Thus, the Banach of the endomorphisms over H script is just a little bit identical as before, which is M script identical up to an isomorphism with L script of H script is equipped with the Frobenius-like norm defined as for you all. Nonetheless, having its identity defined as was indicated on slide 47, then the current N script equipped with the norm N begin defines a non-commutative unital real Banach algebra. Notice that we have this inequality, this estimation. With such constructions, we emulate part 1, where 11 is transformed into 13, which by 12 is uniquely invertible over H script. Hence, we have the splitting of the data operator matrix. The applicability of finite dimensional techniques stating that for omega, a real parameter that's not 0, and for the omega splitting described all this written before you all on the slide, is stated by the fixed point iteration of the GJOR scheme whose component-wise version is 14. The convergence of 14 is a priori assumed if, like in finite dimensions, the operator matrix lambda minus k is an SPD operator matrix with omega chosen aptly. But how is that feasible? In fact, we consider defining SPD operator matrices the same as how one does in finite dimensions. Come for chapter 3, section 3, definition 331, which leads to inherently established lemma 2.1. Suppose that 12 holds and that the kernel function is symmetric almost everywhere over square omega squared. Then the operator lambda minus k is self-adjoint, and the data operator matrix lambda minus k squared, as well as the operator matrix lambda minus d, it's a diagonal operator matrix. Is symmetric. Both of lambda minus k script and lambda minus d script are either positive definite or negative definite. Naturally, we then produce lemma 2.2. Provided that lemma 2.1 holds, the two inverses, no, it's actually the first one, it's the inverse of the operator matrix, lambda minus d, and the second operator matrix are respectively either SPD and PD, or SND and ND. N stands for negative, so SND is just symmetric negative definite. It immediately follows that convergence is governed by theorem 2.1. Provided that lemma 2.1 holds, 14 is convergent for all the positive values, omega, that fall within the range shown on the slide. Phase 2. Proceeding to the second phase of the alteration procedure, we discretize 14 using the projection endomorphism pi sub n over the interval I of L calligraphy sub I, where it's defined by that formula, where the family of these polynomials denotes the omega sub I family of phenomenal legendous polynomials such that the span of it is dense in L calligraphy sub I. Hence, the discretized GJOR sub n scheme is given component-wise as 15. By the properties offered by the Banach algebra and script, especially the spectral ones, the use of characteristics of pi sub n I, especially that of the orthogonal decomposition, we have L sub I is decomposed orthogonally, as shown, makes the induction concept viable to prove the ensuing. Theorem 2.2. Provided that theorem 2.1 holds, the sequence of function vectors U sub n k convergence in the H script norm to the solution function vector of 13, equivalently of 11, and we write the double convergence with respect to k and n, and we have a convergence towards 0. Some numerics. We awfully apologise for the utterly intimidating inconvenience of failing to deliver concrete numerical examples due to the ongoing scrutiny and investigation of implementing the proper algorithmic procedure to fulfill such an machine. Consequently, part 2 ends here. And part 2. A little short memory, a recap. Ultimately, please do remember that our presentation attempted touching upon the following concepts. Regardless of the class, integral equations over large domains or intervals should be approached uncommonly. Adequately break long-standing conventions, ease to venture into new areas. Namely, comfortable as you are with venturing into Banach algebras, the alteration should be a go, given its verifiable superiority. With the right instructions at hand, one can very reasonably extend finite dimensional results into infinite dimensions. Before you and I go, of course, apart from the perplexing invitation offered by the stability of quadrature rules used in part 1, and despite the GJOR's purpose finite dimensionally or infinite dimensionally to serve relaxing the sort of Jacobi's procedure to accelerate it, or even make it convergent, relaxing GGS with respect to concepts from part 2 remains paramount goal because of the ultimate acceleration effect gained. In fact, we conjecture that linear algebra results could and should be seamlessly stretched to have it asserted that with lambda minus k calligraphy, it's the data operator matrix, BSDD, and with omega fallen in the open interval 0, 2, the GSOR is also convergent, identical to how it is the case in finite dimensions. It is still a perspective. In the end, the very quantum reality we live in and the circumstances at one's disposal suggest that perhaps textbooks, theoretical establishments in regards to Rn or Cn could be blended together with advanced tools from functional analysis to set the groundwork for complete theory in the Cartesian product space H, N, and thought. For instance, how likely would it be to succeed at generalizing Geschwin's disks from matrices of bounded Underlösungen over H to the power? It's not a power, it's a thought. The end. Thank you.